Chapter 1, Section 2. Why is linear algebra essential in data science? In this video, let me show the importance of linear algebra in data science more concretely. An essential feature of linear algebra is that it deals with linearity. Linearity refers to a system in which the change in output is directly proportional to the change in input. By introducing the concept of linearity, we can simplify complex problems and make them easier to solve. When something changes linearly, we can accurately predict its outcome. And we can expand or change things without changing the underlying structure. This property makes linear systems easy to understand and also efficient to compute. So, what role does linear algebra play in data science? One of the core of data science is extracting insights from data. A useful mathematical technique for accomplishing this is linear algebra. First, consider how you store your data. When working with large datasets, the data are often represented as matrices. Each row of the matrix represents an individual observation, and each column records the features of an individual observation. This form of data representation is the foundation of machine learning and data mining. Next, consider the concept of similarity. How can we determine if two observations are similar? One of the most common methods is to compute the Euclidean distance, a linear algebra concept. Another example is dimensionality reduction. This is a technique used to reduce the number of variables under consideration. One such method, principal component analysis, is built on linear algebra concepts such as eigenvectors and eigenvalues. In machine learning, many algorithms are deeply rooted in linear algebra. For example, linear regression involves finding the straight line best fits the data. This is done by solving a system of linear equations, a fundamental problem in linear algebra. Thus, linear algebra concepts have applications in the field of data science. Let's continue our discussion about the role of linear algebra in data science. Specifically, let's focus on representing data with vectors and matrices. In data science, vectors can represent data points or observations. For example, consider a dataset about height and weight. There is information about height and weight for several people. We can represent each person as a two-dimensional vector. The first dimension is the person's height, and the second dimension is the person's weight. So, if a person is 180 centimeters tall and weighs 70 kilograms, the person's data can be represented as the vector 180 and 70. This representation allows data to be manipulated, compared, and visualized using linear algebra techniques. A matrix, on the other hand, can represent a collection of these data points or observations. Suppose you want to collect height and weight data from several people. In that case, you can create a dataset that represents each person as a row of a matrix, with each person's height and weight as columns. In this case, the dataset will be a two-dimensional matrix. Each row represents a person, and each column represents a different feature. In this example, the matrix looks like this. By representing our data as vectors and matrices, we can leverage linear algebra to manipulate and understand your data. Next, let's look at how linear transformations can help pre-process and manipulate data. A linear transformation is a function that manipulates a vector to produce a new vector, while retaining the operations of addition and scalar multiplication. In later lectures, we will discuss linear transformations in more detail, so a rough understanding is sufficient here. One of the most common examples of a linear transformation in data science is standardization and normalization as data preprocessing. Standardization is sifting and scaling data so that the mean is 0 and the standard deviation is 1. Standardization is done by subtracting the mean and dividing it by the standard deviation. These operations, subtracting the mean and dividing by the standard deviation, are types of linear transformation. Normalization, which scales a variable so that its values fall between 0 and 1, is another operation performed using linear transformations. These transformations can improve the prediction accuracy of machine learning models. Another common use of linear transformations is feature extraction, including dimensionality reduction. For example, in principal component analysis, a widely used method of dimensionality reduction, a series of linear transformations are performed to rotate the data and align it along the direction of maximum variance. It removes redundant information and focuses on the most important features. As described above, we can build more effective models and make better predictions through linear transformations. Let us now look a little further at the importance of linear algebra in machine learning. Machine learning is a branch of artificial intelligence, a field that uses statistical methods to give computer systems the ability to learn from data. Linear algebra is utilized in almost every part of machine learning. First, data representation in machine learning is based on linear algebra. Specifically, we can represent data points as vectors and datasets as matrices. These representations allow us to manipulate and process data efficiently. Many machine learning algorithms also rely on the concept of linear algebra. For example, consider linear regression, one of the simplest and most widely used machine learning algorithms. In a simple case, linear regression models the relationship between two variables by fitting a linear equation to the observed data. To find the optimal regression line, it is necessary to calculate the values of the parameters that minimize the error. It requires solving simultaneous linear equations, a fundamental problem in linear algebra. Also, in deep learning, an advanced area of machine learning, all operations performed in neural networks are matrix operations, the basis of linear algebra. Since linear algebra is the backbone of machine learning, an understanding of linear algebra helps to understand how various machine learning algorithms work. Thank you for watching. Please thumbs up and subscribe to my channel.